There are some people who have gone to the waiting lobby. Okay. So now it has started recording. I hope you will you'll find it useful. So I will continue now. So like we said, principal component analysis is simply a technique that tries to reduce the dimensionality of your data by transforming the initial data set into a smaller set of uncorrelated variables, and still retaining most of the information in the data. So initially, the transformation does not give you a smaller set, but it gives you a way of throwing away some of the information and being able to measure the extent to the importance of what the remaining variables, the importance of the remaining variables. The importance here is measured in terms of variance, the amount of variance explained. We shall see the details of that shortly. But I suppose that is not entirely new to you. So what I'm saying should make sense, I think. So it started a while back. It's much older than us. So it's just that these days we have computers, so we can do a lot more with it. These are some of the applications. You can do some feature extraction, and you're able to do some graphing and interpret the data. It can help with the situations where you have to classify data, like what is it Martin who's working with the credit scores and so on. You can group people into two groups, those who are likely and not likely to pay. And if the variables are too many, numerical variables are too many, you can use PCA to visualize the data, because if there are too many, you can't draw a graph with more than 3 dimensions. So essentially, your data set will look something like this. You have the variables, which we shall call them x1, x2 up to xk. And then we have n observations or n cases. So this is what it will look like. What you are after now, the assumption is that these variables are too many, and you don't want to work with all of them, and therefore you must find a way of determining what to throw away and what to keep. As they are, you can't easily tell which is the most important variable or which is less important. And then secondly, you may find that a lot of these variables are correlated, and therefore there's some redundancy in the data. So by using PCA, you're able to reduce that redundancy. So essentially what will happen, you will convert these initial variables, the initial set of variables, you're going to convert them into a new set of variables and each of these new set of variables will be a linear combination of the original variables. I think someone is trying to join. I heard a bell ringing. I think there's a way to someone called Brian trying to join. There. I've joined. So what will happen is we'll create the same number of variables as we had initially. We had k variables. We're going to create another k variables. We'll label them as y1 up to yk. And how we get each of these variables is to write them as a linear combination of all the variables. So each of these variables, the y's, contain information about all the original variables. Now, these coefficients are the ones we wish to determine. There's some optimization. So this course is about optimization, although now we shall not look at the details of the optimization. On the optimization, that is applied here is to determine these coefficients under certain conditions. The conditions is that these variables will be uncorrelated, and that they keep reducing in the variance of each of them as you go up gets smaller and smaller. So the variance for y1 will be bigger than the variance for y2, and so on. And the last variable will have the least variance. And based on that, the first variable accounts for more variance in the data, followed by the second, and so on up to the last. And based on that, you can now rank the variables and select the ones you wish to work with. And that way, because they are ranked, you can tell how much information you have retained and how much you have lost. Are there any questions on this one? But this should be familiar because you said you have done PCA. Is there anything that is strange on this one? So I think at some point I will prepare the notes where you see how which illustrates, shows the optimization, the actual process. So the optimization is supposed to get these coefficients satisfying those conditions. We'll look at that later. So after you transform the data, you end up with a new data set, the same size as the original one, but now ordered in decreasing importance. So the first variable is the most important, the second is the second most important, and so on. Where the importance here is determined in terms of the variance of the variable. So that is illustrated by this. You can see the variance of y1 is bigger, and so on. It goes on up to the smallest variance, being that of yk. So that way you can determine which variables are important before you put it. Then the other thing we need to establish, or rather observe, is that these variables are uncorrelated. The new variables are completely uncorrelated. I think someone else is trying to join again. Let's see if we can admit them. But Kasim was in before. Maybe his connection dropped. So this is what will happen eventually after you construct these variables. So now we have explained the overall picture for the transformation. Now we can try to understand how is this transformation done. So the initial data set, we shall choose to represent it as this capital X. So X will be the matrix containing our original data set. It has k variables and n observations, or n cases. So we shall represent the transformed data with this capital letter T. So the new data set will be this capital letter T. So this is your new data set, capital letter T. We'll use that letter to represent it, and this is the old data set. We shall use X as our label for it. So as a matrix, you can do the following transformation. There's this matrix V, which will be a square matrix. So this is it has k variables, so V will be a k by k matrix, and it's an orthogonal matrix. Now, how you obtain V is through the singular value decomposition. I'm assuming you are familiar with that. The singular value decomposition of X will give you V, and normally you will have to scale X so that the values have mean 0. So you are not really responding at all when I ask a question. You're familiar with the singular value decomposition?
Yeah.
Good. So how does singular value decomposition work? How do I obtain V? What do I do to X to obtain V? You don't recall? So V is okay. For now, we just assume it's a matrix, which gives us transforms X into the new variable set of variables. This matrix into this new data set that contains the transformed variables. So after you do the transformation, the eigenvalues now will just be the variances of each of the principal components. The eigenvalues are the I think I can try, after this, we'll try to go through the mathematics behind it so that we see whether you are up to speed or not. So for now, we just have a matrix V, which is obtained through singular value decomposition, and it will transform X into a new data set, T, which consists of variables that are increase in variance as you go further into the file, the data set, and they're uncorrelated. For now, I think that's the most important bit. So these are the process, what you do to the data before you pre-process it by scaling, so that each variable has mean 0 and standard deviation 1. There's also another reason for scaling, and I think when we're doing when we're running the code, we shall show why this is important. So T is supposed to be the same size as X, because the new data set has exactly the same number of variables as the original one, but like you said, these ones have been ranked in some sense, and therefore we can throw away some and know exactly what we have thrown away and what we are keeping, and we end up with a smaller set of variables, which still has sufficient information. So the entries in the new data set are usually called scores. So for each measurement, a score will be computed, and it becomes a new value for each of those measurements. The score is computed using I showed the transformations earlier, how you write y1 up to yk as a linear combination of the initial variables, x1 up to xk. So usually the first two principal components will have the most variation if your data is right, and therefore you can use them to visualize your data, because then once you're able to visualize data, you can pick up any patterns that appear in the data. You might be able to tell if there are clusters based on your data, if it's possible to classify, or you can compare some of if your data is labeled, you can now color the points using the labels and see if the clusters actually make sense. The clusters determined by the labels. So at some point, you'll have to determine how many new variables. For visualization, you can go up to 3 variables. It's not, but it's harder to visualize 3-dimensional data. So most of the time, 2 dimensions is sufficient for visualization. Though if you have, like MATLAB is capable of doing good visualization for 3-dimensional data, sometimes that is helpful. but sometimes it is not. So it's best to just see what you can do with the, for visualization purposes, what you can do with 2 dimensions. For other purposes, you may use more than 2 dimensions. So usually there's a script plot which tells us how much variation to how much variance is represented by each of the principal components. I think that's the previous slide. I think we shall see that as well. Again, I think this is not new to you. So these are the details if you want. I think those are not important to you. So we are going to look at some examples, quickly look at some examples. So one example we'll look at here is this one that aims to investigate the physiochemical. I think it's supposed to be physicochemical, I don't know. Most of the times when we work with this, we have to work with people with a domain expertise. In this case, the people who would be able to help more understand what some of these terms mean are food scientists. But we have a chemical engineer, so maybe he might understand some of this. My expertise is mostly with the numbers, so I may not be able to explain these variables as well because I'm not a food scientist. But this is an example from food science. So here what we have is there are two types of flour. There's one flour that is made from banana pulp, another type of flour that is made from the banana peel. Now, this is done for green bananas, and it's also done as well for ripe bananas. The variety here is a Cavendish bananas. So the aim is to compare these different pulps and see if they are really different based on the variables that have been created. So the variables that were measured, we have the acidity, this pH, you have these total soluble solids. In the data file, it's labeled as TSS. Then we have water holding capacity at different temperatures. So at 0 degrees, water holding capacity and oil holding capacity as well at different temperature, 40 degrees, 60 degrees centigrade, and 80. I left out the degrees here. It's supposed to be degrees centigrade. So we have those variables. We shall see the file shortly. Then there are some other variables that measure color. I don't know how they measure color. Maybe the chemistry guy can help us understand this. Any chance that you, chemical engineering guy, are you familiar with how color values are measured? So
yes, when you want to measure color, most they use spectrophotometry.
Yes.
Or something that we call color meters. So when you use something like the spectrophotometry, then we refer it to the color charts. So different colors are associated with different aspects. So now the color chart helps us to determine the extents of what the color speaks.
So I think these variables, L star, A star, and B star, they refer to some colors. I don't know what, some color values. I don't know what those values are, but they refer to some color values that are measured from, so maybe through that spectrometry. Then there's also one other variable called the back extrusion force, and then the viscosity. So maybe the only variable I can make sense out of here is this acidity. This is the only one I'm familiar with from my high school chemistry. So again, like we said earlier, there are 4 types of flour. The flour that is made from the green banana peel. the flour that is made from the ripe banana peel and so on, the flour that is made from the green pulp and also the ripe pulp. It's always important to understand the data quite well before you move on. So this is a snapshot of the data file. There are all these variables. We have the acidity, the total soluble solid. This is the L, A, and B, those color values. No idea what they mean, but there are some variables there. Measurements rather. Then we have the water holding capacity at different temperatures, the oil holding capacity at these 3 different temperatures, then viscosity and texture, or what they call the back extrusion force. So we have 13 variables. This is quite typical. It's too many. In fact, sometimes even 4 variables can be a problem for us. But here we have 13, and we still want to understand this data. So how do we make sense out of it? We must find a way to reduce the dimension. So if you compare the variances of the original data sets, you can see some are extremely way bigger than the others. So this might exaggerate the importance of some of the variables. So to be able to make them comparable, we standardize the scaling that we talked about earlier. We standardize, we make the mean 0 and variance 1. So the other thing we can look at is the pairwise scatter plots. We pair the variables and plot scatter plots for each of the variables, since they are all numeric variables. But here we have done it for just the first 4, I think. First 4 or 3? The first 4. Just the first 4 variables. There are 13, so if you draw all of them, it will not be a very decent picture. But there are ways of visualizing high dimensional data in R. Are you familiar with Plotly? There's a package called Plotly. You're not familiar with it? Oh. Yeah, so if we have, this is, here we had only 13 variables, but if you have to do this visualization for, say, like 100 variables, it becomes impossible to keep track of anything. But now you can also check the correlations. These are the correlations. We have some high ones, like 0.9 here, it's negative, but close to -1, so that means it's a high correlation. 0.34. So these high correlations are good for us when we are targeting principal components. The other thing we can observe from these scatter plots is these different colors represent the different banana classifications: the green pulp, the ripe pulp, and then the green peel and ripe peel. They are not labeled here, but each color represents a different variety, flower variety. So you can see there's some clustering that is going on. So already we're able to see the patterns, but they vary depending on which 2 variables you're looking at. So if you look at these 2 variables, the total soluble solids and this color variable L, it looks like there's quite a bit of it's very clear separation of the 4 different flowers. So you may be able to, tells you this is a good candidate for classification. And maybe if you are looking for clusters, maybe you should look for 4, because the principal component seems to suggest that there are 4 clusters. Not the principal components, just the basic plots, the pairwise scatter plots. They seem to suggest that there are 4 clusters. In some cases, they are a bit mixed. In some cases, for some of the variables, the clusters are quite clear. For some of the other pairs, they are not so clear. So, but this gives you a rough picture of what is going on. As a chemist, maybe this might make sense. And if you look at the corresponding, what do you call this? The histograms, they also seem to be bimodal. along the x-axis. So it means it's possible that one side represents the green or ripe, or it might be presenting the pulp variety or the peel variety of the flour. But you can see a lot, they are bimodal or multimodal in some cases, but basically bimodal. If you look at the density plot, it suggests two different distributions. This one as well. This one is not quite clear, but they're like two major peaks. Is that making sense?
Yes, it's making sense.
So am I moving too slowly, or should I double the speed? You know, you might be dozing on that side, and I'm assuming you're following.
But the speed is okay. You should double.
Okay.
Yes.
So this is just another way of representing the correlations. Now you can see all of them. And of course, there are quite a number of fairly high correlations. There's 0.5, there's 0.6, 0.7. So this is a good candidate for our work. The high correlations mean there's a lot of redundancy in the data, which we can take care of by getting new variables that are not correlated. So this is just, are you familiar with this kind of diagrams? So this is the output for the principal components analysis. If you run it, this is the output you get. I don't know whether you did this in Python or in R.
Python, not R.
Python.
So you don't know how to do it in R. And when doing it in Python, did you do the computations from scratch, or you are using the functions in Python, the inbuilt functions in Python to run the PCA?
I believe we're using the inbuilt functions.
Okay. So I have not written the code for doing this in Python, but you're already familiar with the code. But so maybe the output might look a bit different. Now you can see what has happened. We have all these components all the way up to 13. So this, what appears as component 1, component 2 here will be the, what do we call them? The new variables. So what we're calling Y1, Y2 up to YK are these new variables. So we'll have 13 of them. And then we have the standard deviations for each of them. And these are already standardized. Standardized means they have been scaled so that they're comparable. Each of them has a proportion of variance that it explains. Right in the second row, this continues all the way up to the 13th one. But our column of interest is this last one, which covers the cumulative proportion of variance explained. So you can see the first component explains about 45% of the variation. So already with just one component, we have almost half of a variation. By the time we get the second component, we have 75%, close to 75% of the variation in the data explained. And by the third, we have about 87. So we have, with just 3 components out of 13, you have 87% of the information that you need from the data explained, where information here is measured by the variance explained. So that means with just these 2 variables, component 1 and component 2, you still have quite a chunk of information about the data. And if there are any patterns that are picked from that were in the data are available, you should be able to pick them up with just these first two components. So let's see. this is what the this is the so remember these coefficients, the AI1. I'm wondering whether I should go back to that slide, or we'll get back to that in a short while. So this row, this row that shows the cumulative proportion of variance explained can be captured using this script plot. Of course, you can have the labels to show the actual values. This one doesn't, but that can be fixed. So the first variable is the one with the highest, the second variable, the next second highest, and keeps going on. By the third, we have most of the variation, and a number of these may just be considered as noise. It may not mean much. There may not be any strong signal in this remaining principal component. So if you stopped at four of these alone, for instance, if you are doing something else that is beyond visualization, you can just work with those first four, and you still have quite a bit of information in your data. So if you are running some classification algorithm, you can end up just working with 4 variables instead of working with 13, and that can make a big difference in the efficiency of your application. So these are the coefficients. I will let me just go back. So first, think of this as Y1, and these are the corresponding coefficients that are used to transform the original data. Although it's not quite the original data, we'll use this to transform the original data after it has been scaled. Is that making sense? You have to scale the data first before you transform it. So what we are calling the original data in this case is the scaled data, the one that has been transformed to have a variance of 1 and mean of 0. So pay attention to this. This is think of this as a variable Y1. The rest will be all the way up to Y13, but just focus on this one. What we're going to say applies to all the others. So all these coefficients, 13 of them, these would appear if we go back to our slide. So these would be these coefficients, A11, A12, and K is 13. So it will be up to A1, 13. There'll be 13 of these coefficients for each new variable. So those are the ones that appear in this table. So here they are. You can now pull them out as loadings. There are other packages which are can do principal components analysis, but this one is simply based on the one that comes out of the box in R. Just no, you don't need any new package to run this. I think this is correct, is it? Yeah, I think this one you don't. I will double check. There's another one also called PR comp. So I'm not sure whether this is the one that works from the base R or you need a package for that. Whatever the case, I think I've explained what these are. These are now those coefficients. So for each of the variables, it will have its own coefficients. These are the ones used to transform the original data file. Now, if you are interested in feature extraction, this might be of use. You may look at the first principal component and see on which variables it loads heavily. So you can see where heavily maybe would be something like 0.3 or higher. So this first principal component doesn't seem to favor any variables explicitly because it loads, if you look at texture, it's 0.3. The oil holding capacities are all about 0.3 roughly. Same for the water holding capacity. So it seems to be a general feature that explains everything. Doesn't seem to favor, with the exception of acidity and these total soluble solids. These ones don't seem to be represented in the first principal component because their coefficients are quite small. Maybe also this other color component. There are these two color components which seem to be strong, though in opposite directions. They are strong in the first principal component. The second principal component seems to be strong on the total soluble solids. And then it's a bit high on the water holding capacity compared to the oil holding capacity. So maybe this one separates these two aspects, the water holding capacity and the oil holding capacity. So you may assume that that feature, as well as viscosity, you may assume that this oil holding capacity, this component differentiates between these two, water holding capacity and oil holding capacity. I don't know if I'm making sense. I'm talking and talking and talking. I need to know if I am making sense.
Yes, you are.
Yeah, so you could do the same analysis for the remaining components, but usually the first few are the ones that have useful information, maybe up to the fourth or fifth, but it's not an exact science. Sometimes there might be some components which are further to the right that have low scores, but if you plot them, they might still have some structure. They might still have some structural information about the data. So that one, you can discover that through exploratory data analysis. So before you do your analysis, you might try to plot some of the other than the first two, you can try to plot other pairs and see if you can still pick up some information. So this is now the transformed data. This is what we call the matrix Y. If after the data is transformed, this is what it looks like. So I just remember these were the loadings. These are the coefficients for in the matrix V that transforms the data, and this is the data after it has been transformed. So if you are interested in, if you extract this matrix and multiply it with the scaled data on the left side, right side of the scaled data, you should end up with this new data. So these are the new variables after transformation, and each of them, they are uncorrelated. You could also check that by simply computing the correlation between any pair of variables in this file. Now you will see that the correlation is really small, very close to zero. So what happens is with these new variables, you can plot the first two only, what we call the first component and the second component. So you use just these first two columns. Earlier on, we saw that they account for, the first two account for about 74%, which is really high for purposes of visualization. So as we visualize, we can be sure we have quite a bit of information retained from the original data. So I'm not sure if I labeled this correctly. There's a time I was going through the code and I had to make some corrections. But you can see clearly when you plot the first two principal components, the, what do you call it? The first two principal components, you can see the clusters very clearly. There are 4 separate clusters, and each flower variety is in its own cluster. There's no overlap at all between the clusters. So this tells you that this is almost perfect classification. If you are to use some of the classification algorithms, it should work quite well. So now you're able to visualize the data, and you can see that based on the variables that you have, it's actually possible to cluster them. Now, principal components analysis is not ideal for clustering, but it's good for not ideal for clustering and classification, but it's good for visualizing the patterns in the data. So now with this, you can go further and do some classification using other techniques. Are we together? So
yes.
we are plotting these first two columns, PC1 and PC2. So that brings us to, this is a complete application on a data set. Maybe the one thing we have not looked at is the biplot. Maybe it's further ahead, I'm not sure. But based on this now, if for instance, someone came with some flour that you are not able to identify, it may be one of these four, but you can't identify it and you wish to identify it, you can take the measurements and standardize them. So this one are the standardized measurements of some unidentified flour. And once you have them, you can transform them and plot. You can fit and plot them on this graph. So you can see this new data set, which we picked, landed on the green pill. So we can easily, we suspect that it must be of a green pill variety, because after plotting it into this graph, this is where it landed. So this has to go through the transformation. It has to be projected. So what you're doing this, I think, I don't know if you learned about projection. You are basically projecting this onto this plane. If projected onto this plane, it landed here. Projection is from linear algebra. You're familiar with projection? You are quite hesitant to speak.
Not familiar with that, Dr.
Hey, yeah. Okay, that was my fear with the mathematics. So if I go into the mathematics, I think we may have to go far behind for it to be, but we will figure out something that still shows us how the optimization is applied in this. So this is a biplot. The same feature. So you can see like the oil holding capacity, they are all clustered around here. The water holding capacity clustered around here. So this second principal component we saw earlier seems to separate, it's good at separating it can classify the two. Those with a higher, in terms of these principal components, the ones with the positive values seem to be more of seems to capture this feature of the oil holding capacity. The ones with lower values seem to capture this feature of the water holding capacity. And then one side, I think, is either the pulp. I never labeled this, so I'm not sure what these are. One side must be the pulp, but it's possible to check because these numbers that you see here are simply the numbers of the observations. So like this 46 refers to the 46th observation in the file. So it's possible to check whether these ones are the green pills or the ripe pills and so on. And then the separation. So the first principal component seems to be able to separate these three. 1, 2, 3. The second principal component seems to separate also into 3 clusters, but these 2 are not very different on the second principal component, just like these 2 are not so different on the first principal component, but they differ. The second principal component captures this difference between the 2. The first one does not capture that difference, but it captures the difference between and these other 2. It's able to do that separation for us. Okay, so what is, do you have any questions on this?
I didn't understand what you meant by the first component analysis can separate which clusters exactly. Maybe you can explain again on that biplot.
The biplot is not different from the scatter plot we did earlier. Let me put it back on presentation mode. So if you look at the information I'm giving you, you didn't need the biplot to get it. You can actually get it from here. So you can see if you go along this first principal component, this variety seems to be within some limits, not very far from 0 around here. It scores quite low, right? So if you transform some new data that you have received and it lands around here, you may consider it as a green peel flower variety. If it scores around here on the first principal component, if it scores around here, you may think of it as a ripe peel flower variety. If it scores towards the right, you'll think of it as a green pulp variety. But if it scores around here for the ripe peel, you may not be able to differentiate it from the ripe pulp because these ones, you can see they all seem to score around the same value. Between say this one and this one, because this one seems to be somewhere midway. These ones somewhere high up in the positive side, and these ones are towards the large in magnitude but negative. So the second principal component is able to separate these 2 flower varieties.
Okay, yeah, makes sense.
Yeah. So it's just based on observing the measurements. This one seems to score higher on the second principal component. This one score lower.
All right, thank you.
Okay. So they are, I think that's our first major milestone we can celebrate. I don't hear any celebrations though, but.
Oh, yeah.
Are there any other questions? So there are 2 other applications that I looked at in this presentation, but now we will see them when we work with the data. So the 2 other applications are this. This one is for political science. It was able to classify some, or rather it seemed to pick up some 3 clusters based on some survey that was done to get some people's attitudes towards political stuff, the judiciary, whatnot, and so on. We will see the data when we work with the, when we go to the coding. But you see, it was able to classify the people into 3 different political groupings.
Doctor, I have a question.
Yes.
Okay, how does the PCA handle outliers? Because based on the graph, like now this one that we are seeing, I don't think it's representing outliers. How will it handle outliers? Or maybe you can explain.
So outliers, PCA is actually used for, it can be used for identifying outliers. If you have a data set with many variables, it's very difficult to identify an outlier by just looking at the data. But now you can see points like this.
Okay.
You can now go back to the data file because they are quite separated from the rest. There's something I mentioned earlier about this transformation being orthogonal. Did you learn about orthogonal transformations in
Yes.
linear algebra?
Yes.
So orthogonal transformations, I don't remember where I wrote that. This V, you see, V is an orthogonal matrix. So an orthogonal transformation preserves distances between points. So even the points that are far apart in the original data set will still remain far apart. Those that are near, close to each other, will still remain close to each other in the new data set. So if there are any outliers, they'll be picked up. If they are far from the rest of the points, they will still be picked up by the visualization.
Okay.
So if you are interested in finding outliers, now you may want to find out these points. What are they? You can actually pick them up and go back to the data, and you can pick. It's possible to find them in the data. So you can what do you call it? You can find outliers using PCA, because if you have like 100 variables, there's no way of just looking at the values and calling the observation an outlier. But now in 2 dimensions, you can tell. I'm not sure what your question was about how you handle outliers, or whether it has been answered.
I think basically it's what you have answered. I think based on what you have been defining, I didn't see a case where there are outliers, so that's why I was worried about it.
So they are outliers, like this one. These 2 points seem to be quite far removed from the rest of the data. The rest seem to be fairly close. You will not always get outliers, but it's possible to generate do a simulation of a case where we can check the effects of outliers. Now, if the outliers are many, also they affect the quality of your principal components analysis. You can also check for outliers for individual variables using you can use the box plots. You know how to use box plots?
Yes. Yes.
Yeah. So using box plots, you can check for outliers for individual variables. So if there's any particular point that is an outlier, it actually affects the quality of your PCA. But for visualization purposes, I think usually most of the time you'll be fine. Now there's another type of components analysis called the robust principal components analysis, which handles outliers better. I don't think we'll do that, but you can go and do some research on that, the robust principal components analysis. Now the maths involved in that one is again fairly advanced, because the metric, sometimes they use a metric, not a very common metric, the L1 metric. Most of the work we do, we use the Euclidean metric for distance. But for that one, I think the metric is different. It's L1 is, I don't know. I don't want to go into them. Did any of you do real analysis or topology? in real analysis, you learn about metrics or metric spaces. So there are different types of metrics. There's a L2 metric, which is just the Euclidean distance. Then there's a L1 metric, which is what is used for optimization in robust principal components analysis. But we'll not go into that. We'll leave it out. So this is another example which had almost 30 variables. And after you apply PCA to it, you're able to clearly see that it's possible to classify the benign tumors from the malignant ones. Many of you may be familiar with this dataset. It's a publicly available dataset, the Wisconsin breast cancer dataset, some American university has it in their repository. I think it's also available. If you just search for this online, you will find this dataset. It's publicly available. So you can use this for the credit scoring data as well. It can be helpful. Was it Martin who was from the bank? I'm trying to remember. Working on credit scoring. This can be. I have some data on publicly available data on credit scoring. So maybe later on we can use it. You can also apply principal components analysis to images. And in this case, we are using it to find an outlier. So in this case, if you look at this picture, there is a small metal pin here. I've put a white square around it so that we can track it. So a small metal pin here, which is not easy to see. It's an outlier. But if you use principal components analysis, it is picked up as a small dark spot here in the second principal. There's a first principal component, and then the second principal component. You can see this one picks out the lighter colors. This one picks out the darker colors. I don't know if you worked with images when you're working with the principal components analysis, or what objects or which data did you work with?
Yeah, images was one of them.
Yeah, so but you'll notice it's the images are rotated after you run them through the analysis. They are rotated. It's not facing the same direction as the original one. So that can happen as well. You need to keep, so that's why you see at this point, this square is here, but here it has been rotated. So sometimes the data is rotated and may not face the same direction as the original. So I don't know, maybe we can, it's already 7:30. We can take a short break. Is that okay?
Yes, we can take a short break.
Is 10 minutes okay? Then we quickly try to go through the code, the R code.
Yes.
Okay, so we resume at 7:40.
Okay.
I think we're all back now. Sharon, maybe you need to put off your microphone. So I'll share my screen again. So I don't know if you can see my.
Yes, Dr. We can see your screen.
Okay, so this is the file itself. The data is in a folder here. And we have saved it in an RDA file. So we just load it. Then we can view. I was planning to convert this into a R markdown file, but I never did. I did this a while back before I knew how to work with a markdown file. So it works better if you move it to a markdown file. Maybe in future I will, but it doesn't matter. You can do that yourself. In time, for now, we just need to understand what's going on. So we've loaded the dataset that contains the information about the physiochemical properties of this banana pulp. Then we've looked at the first few rows of the data. We had already described this earlier, so I don't know if there are any questions about it. I think the next line just computes the variances for each variable. Then the next one plots the variances, and we see that there's a wide variation between the variances. Some are really small, some are really big. So that's a good reason to do standardization. Yeah, I mean scaling. It's a good reason to do your scaling, so that your variables have mean 0 and standard deviation or variance 1. So for some of the things we want to do, we will need this psych package, which is, I think I hope I've already installed it, but we'll just load the psych package. You're familiar with R as well, so I think what I'm doing will, someone I think is trying to join. Let me see if I can get them in. So this psych library, you don't need this for this next command. This one comes from the base R, just out of the box. You're able to do these pair plots. I think the next one is where we will need the psych package. So this is the basic pairs plots. We had already seen this in the file, but here we have just done it for the first 3. You can get the histogram of one of the variables. This is just exploratory work. You could do this for more of the variables, but you can see again there's 2 separate clusters just based on the total soluble solids. There are some that score quite high and some that score quite low. So if you want to do some exploratory work, you can proceed and do that for the rest of the variables. Then the next one is simply a pairs plot, but now with a little more detail. So this is where this pairs plot is what comes from this psych package. So if you run this one, you should see the same pairwise scatter plot. Something is not working. This is supposed to color the points. Just a minute, let's get rid of this. See if it makes a difference. Yeah, now they're colored. Or oh, I made a mistake. I've asked it to run the rest of the file. I intended to press Control Enter, but I pressed Control Shift Enter. I should interrupt this. I'll stop it. Stop. It's not listening to the stop command. Okay, let it finish. We will. Okay, I think it has run all the things. I can now continue. So let's try this and see if it works. Yeah, I think there's something I'd added there that was not supposed to be there. Not sure what was going on there. Anyway. So now we can see the colors. It colors based on the varieties. So this will order them the way they are in the. No, this doesn't work. I'll have to go back and check what went wrong here. It's supposed to color this based on the groupings in this variable, this group variable, but it is not doing that. The first one worked well, but this one doesn't seem to be fine. Let's check the structure. Maybe we need to turn one of the variables into a factor. You can check the structure of the file. It's already a factor, so it should work. Okay, I'll not try to fix this now, but the basic idea was to color. I'm not sure what changed there. I've used it before. Ah, now it works. Hi, okay. No, that was the pairs one. So I'm looking at the wrong one. The next one was this. Yeah, now it is working. Why wasn't it working before? I've not changed anything. I've just put back the same. That's the problem with coding. So now it's working, but it's the same pairs plot. So the only difference is now it adds the histograms for each variable. Now we are just plotting the first 4 variables, and then it also gives you the correlations between the variables. If you want more, you can add more variables from the graph, from the data set. So the other thing you normally look at are the correlations. So this next one just gives you the correlation matrix. And here it is. So you can see this, the correlation matrix, but this one is has too many figures to look at, so may not be easy to study. We can use this package called CorePlot, and we can put in the input can be the correlation matrix. Then it gives us a better way of visualizing the correlation using these bubbles. So using the bubbles, but it also puts in the values on the lower side. And on this side, it's using the bubbles and the gradient scale here to show you the level of correlation. I think someone has been kicked out again and trying to join. Let's admit them. Is this a person called HNK familiar to anyone?
I think it's Hannah Kamau, but I'm not really sure.
Yeah, because we need to know who is in the. It's important that when you log in with your correct name. So like HNK, I think you should change your name to your correct name so that we know we have the correct people in the class. Who is HNK? Can you identify yourself? If you're not able to identify yourself, we may have to remove you from the class. Ametoka. Yeah, you know, with these online classes, you never know. You can have people with bad intentions in the class. So here is a command that runs the principal components analysis, this print comp. You don't need any package for that. Or I don't know if it comes from the psych package. It may be from the psych package. There's also another one which comes from the basic R. If you want to know whether it works without, you'd have to run it without loading the psych package and see if it works. But for now, we already loaded the psych package, so maybe it's from there. I'll have to check to verify that later. So the correlations, you can check and see the ones that are high, the ones that are low, and so on. It's not of much interest to us now, other than to show that there are some high correlations. So we're going to run this principal components analysis, and then we will store it in this variable PCA, and then we can get the summary. So I've run the PCA, specified that correlation is equal to true. This ensures that our data is scaled before the analysis is done. And this is what we saw in the slides. We have the standard deviation for, these are now the eigenvalues. These standard deviations are actually the eigenvalues. And then this measures, the eigenvalues are supposed to be the variances for each component. And this gives you the proportion of the variance that is explained by each component. It keeps reducing as you go further. And this is what we saw earlier, that by the third component, you have about 87% of the variation accounted for. So you can obtain that by putting this object into this function, script plot. It can plot the. Now, this was set up to show nothing on the x-axis as well as to show no labels on the y-axis. But basically, these are the variances. You can change that later to if you want the figures to appear. So this was just to visualize without the numbers. So these two options are the ones that remove the numbers from the axis. You can remove them, then you will be able to see the numbers. So this is if you want the singular values, and the variances are just the squares of the singular values. The eigenvalues are rather squares of the singular values. Now, singular values are the ones, the standard deviations are just the singular values. So the variances are the squares of the standard deviations. All this I'm saying, assuming that you remember what you did on singular value decomposition, and assuming that you can actually connect it to principal components analysis. But if you have questions, and if what I'm saying is not making sense, you need to ask questions so that we, if necessary, we can go to a whiteboard on the computer and do some math.
Dr. Can I interject a bit?
Yes.
Actually, you might have noticed people are quite quiet when you ask questions, especially around SVDs and maybe the eigenvalues. So the experience for the class, especially, was it matrix computation, wasn't quite good. So we pretty much have a very, very rough idea about the, say, the mathematics behind, say, PCA, and I think all that is entailed in this now course, people do not have a good grasp of like the background. So I was requesting if we could have a recap.
So Penina, you probably should introduce yourself. You're not there at the beginning.
Yeah, I joined in quite
You had an
late.
introduction session, so we were making sure we can see who is speaking. Now I don't know who is speaking.
Oh.
If you can put on your camera.
A camera, but okay. Anyway, let me try and see. I'm in a bush somewhere, so.
Okay, we have no problem with the bush.
Okay. You can see me?
Yes, we can see you now, or at least I
Okay.
can see you. Yes,
Okay.
so tell us more about yourself. What is your math background? And I was asking that for everyone. What's your
Okay.
first degree? Is it?
My first degree is in computer science. So.
It's what?
Computer science.
Computer science. You did computer science where?
In PCA University.
Oh,
Long
Kisii.
time ago. Yeah.
Okay. And
Yes.
at least that is connected to
Yes, it is.
data.
Yes.
Okay, you can switch off your video.
Okay.
We just needed to make sure we know everyone who is in class. So I've been asking before whether you understood the mathematics behind this, and the impression I got is that you have understood it. Penina is of a contrary opinion, so I don't know what the true status of this is. Can other people speak as well? Or Penina, you can verify what you mean by the experience was not good. What exactly was missing?
I think the point is, we didn't quite have even. I'm being honest. Maybe other people are not. We didn't have. I think we even had a course outline towards the end of when we were about to do our exams, and the book that was even shared, we had to buy. So it wasn't. Okay, that is me personally. I don't have a good grasp. For me to like get this course quite clearly, I would need some assistance from the matrix computation, because you'd kind of make your own notes. Sorry?
Which book was this?
I can't remember, because even the book was shared towards the end of when we were about to do the exams.
Do you know the author of the book?
I can check from the, or if someone in class can remember the book.
Yeah, it would be good to share.
Yeah.
Even if you just know the title.
Let me check.
It was linear algebra and learning from data, I think, something.
Is that
By Gilbert Strang.
Oh, you do not have to buy that. But it's not the only book on linear algebra. So you probably. So I still don't get the problem. The problem was just the book.
No, not really. Or someone else can speak. I might be just on the extreme end, maybe, if they can.
So Caroline seems to know the book. Can you tell us more about whether you understood what was in the book?
Not really. I think like just what Panina is saying, I think the book was shared like quite late in the semester, and we did not even have a well-outlined course outline throughout the semester as well. So I think people have a sketchy idea of the SVD, the PCA, the eigenvalues, eigenvectors that we may need to apply here. So that's why we. I'm also
What exactly
supporting.
were you doing in class for the? Because you had classes. So what exactly? You don't have notes. You don't have any.
The classes mostly was coding, where the lecturer used to code on a few things or several things. Yeah.
Several things. The coding makes sense.
Yeah, some of it made sense, although it wasn't a very safe space, I would say.
Pardon?
It wasn't a very safe space, I would say that. So that's why I think people maybe had questions and couldn't ask or something.
Okay, you are not allowed to ask questions, or you. Okay, maybe I can ask Rogers to give us a final word. Then we see the way forward.
Yes, Dr. I think I can contribute. Yes, we had a matrix linear algebra computation last semester, but based on my view, what was offered was high level, especially when it comes to decompositions, that is SVD, eigenvalue, yeah, and even the others. It was high level explanation that might have not resonated well with some of us who are actually trying to acquaint ourselves with the basics. Yeah, so yeah, that's the case.
Some of us includes you, or
yes.
So maybe I've just been speaking to myself all through. I thought tuko pamoja bwana. Hey, yeah. This is a bit unsettling. So what do you propose we do? What do you think is a solution? If I
I think that the solution is you could just go, you could just proceed or continue with the way you are taking us, but you could be kind of explaining some of these ideas, like now for this case, but just briefly, not in detail, like for like some of these decompositions, eigenvalue, SVD, yeah. Just explaining, and
they're not things you can, a lot of them are not things you can explain in one paragraph or a few lines.
Yes.
Because they depend on a lot of previous knowledge. So
yeah.
you're going to explain them, the mathematical side, it's not something you can do in a few lines. And it's just not possible.
Okay.
So brief. When you say brief, it may not be very brief.
Because I also know we also read, we can also read for ourselves. Yeah, provided the materials. Yeah, for some of them.
Yeah, but I can only be brief if I know what you have read. If I don't know what you have read, It's very difficult to be, and also, even if you have read, I'm not sure whether you've understood what you read. So there's some balance
I
to be done there.
I suggest maybe a recap if it can be maybe just to understand the concepts, and then maybe as we continue it can be easier for us to know, like I don't know.
Okay, a lot of you seem to have some math background, so you must have done linear algebra in your undergraduate. And some of you are quite recent graduates. So if you have done your linear algebra in undergraduate, then if you sit down with a textbook and be ready to solve some problems, you should be able to do it independently. I don't think we have a lot of time. That's my problem.
Yes, actually already, yeah, 3 weeks are actually gone, yeah, without learning.
So the coming 2 weeks, I don't think we can have any extra class. There's some other things that are keeping me busy. But after that, I think we can have some extra class. But it's good when you speak out, so that I know if there's any problem or not. So send me the title of the book that you are using.
Okay.
I will share. I will try to look for the soft copy and share.
Okay.
And then I will also try to explain as briefly as I can for while we are doing this. So these ones are just showing this next plot repeats the same thing that we've done. It's just doing it in a different way. So here we can load. We can bring these loadings. This I'd explained earlier what the loadings are. Let me run them. Now we can explain them here. So these are the loadings. Remember those coefficients that transform. This is basically the matrix V that transforms the original data. Although the way it is, it doesn't look like a matrix here, but it's because it had to be extended. It had to be extended down here, but it's supposed to be a square 13 by 13 matrix because you have 13 variables. So this one are just those coefficients. You don't need, this is just for your information, but we are not using them directly. They are behind the scenes. So this, we can store the new data. The transformed data is in this attribute, scores. So if I run this, oh no, I need to display it. So if you want to see T, we can type T so that we display it. So this is the data after transformation. So you need to get the difference between the scores. The scores are this data after transformation, and these loadings are just those coefficients that I had shown you earlier in the presentation. So this is the new data set, and this is the one we shall plot these first two components, this one and this one, to get to be able to visualize the data. I will skip these plots for now. So these, maybe I shouldn't. Let's just go ahead anyway. So we can do a bar plot of the first principal component. That's the first column of this matrix T. If you do a bar plot, it will give you some information. So we have colored each group differently. So this is how they score on the first principal component. You can see these two varieties. They score negative and almost the same on the first principal component. This variety scores quite high and positive on the first principal component, because you can see the bars are really high. Then there's this variety which is not, scores very low on the principal component. I think this was the one in the middle, right? Even if you check the scatter plots, it gives a similar picture. Not these scatter plots. I think the one we need to check is the one that comes next. So the next one is a scatter plot. So you can see there are these two which score high on the first principal component, high and negative in the first principal component. If you check the bar plot, there must be these two varieties. Again, I didn't label them, but you can label them. Then you can see this one scores low. This gray one is scoring low on the first principal component. And also if you check your bar plot, it gives you the same picture here. And then there's one, this one in particular is scores high and positive on the first principal component. And again, the bar plot brings that out. This one is positive, but high on the first principal component. So you can do these bar plots for each principal component. I just picked that for the first principal component. So it's like this first principal component is able to separate between these varieties, the ones that are scoring positive and the ones that are scoring negative. But it doesn't do a good job of separating these two varieties, these two. And also when you check the scatter plot we had seen earlier, it doesn't do, the first principal component doesn't do a good job of separating these two. You could plot the second principal component again, the bar plot just of that one only. So to do the second principal component, I just need the second column. So I can change this to 2. There's 2. Get the bar plot for the second principal component. So the second principal component scores high positive for one of them. These two are negative, so it's not able to separate these two. And also low for one other variety. So these two are roughly the same. They can be separated. This is a bit low on the second principal component. This one is quite high and positive. These ones are large in magnitude and negative for the second principal component, and so on. So if you go to the scatter plot, if you look at the second principal component, there's one here which is very high and positive. And again, you're able to see that in the scatter in the bar plot for that specific principal component, and so on. So we can add some more information on the, so this is just labeling. The rest is just labeling the graph to label the different flower varieties. This one will do the same graph, but now using ggplot instead of the basic plot function in R. So using ggplot, I think it's this one. The good thing is it does a labeling fairly well. You don't have to struggle too much with this. This tidyverse package, including the ggplot, assists a lot in simplifying the plotting and labeling. So this one is quite easy to classify because the labels are here. So this orange, is it pink looking ones must be the green peel variety, which are here. This so this one picks up the label straight from the file, so it doesn't make a mistake. So these ones here are the green pulp. So you can see the green ones score quite negative on the second principal component. Right? The ripe ones score on the positive. The one scores low and positive, the other one is high and positive on the second principal component. So it looks like the second principal component is good at differentiating between the pulp variety and the peel variety. Is that correct? Yeah, because these are both pulp. These are pulp varieties based on the labeling here. So now here we generate some new data, but we generate new data which is already standardized. I will run this, then turn it into a data frame. Then I project. This is the projection I was talking about. So I've done the projection there. I will avoid the details because I think it will not make sense. And then I plot the graph again, but then I plot the new point. You see, if I plot the new point, it lands among this green peel variety. So we can classify it as the green peel variety. So that is assuming that you got some new flower, took some measurements, but you couldn't identify what it was. Based on the information you have here, you can try to project it onto these two components, and it lands squarely in the middle of this cluster for the green peel variety. So you cannot rely on this classification, but it gives you a rough idea. If you are looking for exploring options, this one gives you an idea of where of what to classify it as. So the only thing remaining now is the biplot. So the arrows point at each, the arrows will be for each variable, right? So like this variable seems to be associated more with this cluster. They point towards the clusters to which they are more correlated to, right? So this one, this is a color. This one points in this direction, so it seems to capture both these two varieties, stronger in that direction. These oil holding capacities seem to be stronger in this direction. The water holding capacity seems to be stronger for this cluster, and so on. So I think I'd like to stop there for today. Now there's more analysis, but based on a different data set. We could look at this in the next class. In the meantime, I try to figure out a way to navigate the problem of the knowledge from linear algebra. So I think it's better if we could stop here. There's a comment.
Okay, thank you. So you'll share with me that's the presentation and the R code.
Yes.
Okay.
I will do that. and share me with the book title for
Okay.
linear algebra.
I'm going.
Well, I don't know if you also classify my class as a space that is not safe, or I don't know what you meant by a space that is not safe. Maybe we need to bring some policemen to guard the class. Are you okay with the class? Is there, for my class, if you have any questions, do not hesitate to ask, please. So how did you do the exam if you did not understand what you had learned?
Okay, we just read for ourselves most of the concepts. Yes, and then.
Okay, let me see if I can stop recording. So I have stopped recording. I think I will be able to catch the